what I have been doing with my students the last several years. And I'm studying what's known as a partial geometric designs, which is a special family of ordinary combinatorial designs. So I'm going to briefly introduce where these partial geometric designs coming out. And then most of my talk will be a characterization of partial geometric designs which having a certain properties. And then the many partial geometric designs I'm going to discuss this morning will be also coming from association schemes. So we will see some connections with association schemes and partial geometric designs specifically, and construct partial geometric designs from certain family of association schemes. And on the other, and partial geometric designs also and gives us an association scheme. So I'll explain both of those connections. Okay, go to the next page. So our study all stems from when one of my students, Oktay Olmes, recognized that the partial geometries gives us strongly regular graphs and directed strongly regular graphs. So he was so interested in studying and such a nice algebraic graphs. And so when you look at some of those sources of directed strongly regular graph, and he found out that the partial geometry was one of them. And then we think about more general sources of this directed strongly regular graph. So one of generalization of partial geometries are, and what I'm going to introduce today is partial geometric designs. So that has been studied. So if you click the next one, and partial geometric designs, including this one coming from partial geometries, ordinary T designs, and certain symmetric complete bipartite graphs, or transversal designs, and there are many sources of partial geometric designs. So we were checking whether all these partial geometric designs also produces strongly regular graph. So we found one way to construct directed strongly regular graph from partial geometric designs. And then as a continuation, and we want to characterize some of those partial geometric designs, which also having, and not only gives a directed strongly regular graph in that way, but to other combinatorial structures and instance structures. So we look at those other structures, and which I'm going to introduce you, and some of those things obtained from relation graphs of association schemes. Okay, next. So my goal is basically I'm interested in characterization and classification of and some of those combinatorial objects. So this partial geometric design is one of them. So my talk will be focused on the characteristics of some of these partial geometric designs, which gives us a specific other combinatorial structures, such as a directed strongly regular graph or an association schemes. Okay, next. So, and I'm going to briefly recall some of those basic concepts, which many of you are already familiar with, but please bear with me. Finite instance structure is usually denoted as a triples, and point set and set of lines or block set B, and then instance between point and blocks. So the instance I is just a subset of Cartesian product P cross B. So always we're talking about point block pair as a flag if it is inside I, and otherwise, and point block is not instant, such a pair will be called anti-flag. And T design, as you know, if the instance is a natural instance, such as a point and block is in the instance in this instance structure, if point B coming as an element of block and meaning, and all the blocks are subsets of a given point sets. So when we choose block set as a collection of subsets of a point set, and the instance is natural instance, like a membership of a set, then we are going to just delete the instance and we will say pair point set P and block set B is a design. So we call it design when we have such as a particular instance relation where block sets are collections of subsets of a point set. If point set size is V, block set, and there are B blocks, and each block is of uniform size K, and every point instant with exactly R blocks, and then we are talking about a specific type of design, which we call one design, and specifying with these parameters, we call it 1VBKR design, where K is a block size, R is a recurrence of a point in a blocks. And then when you're talking about a T, use ordinary T design with T bigger than or equal to 2. And we're talking about that specific tactical configuration one design and having another additional property. Every set of T points contained in exactly lambda blocks. So when you're talking about two design, every pair of points occur together in lambda blocks. And we are talking about two designs. T design, every T point set contained in lambda blocks. Of course, in that case, T is smaller than the block size K, and to make sense. So our design is, because we are taking block set as a collection of subsets, but without redundance. So we usually call it simple design. So there won't be any repeated blocks in our discussion today, okay? Okay. As a parametric conditions, and every one design, of course, VB is same as BK. Every point occur in R blocks, so VR is equal to BK. And also, if it is a T design, and if we choose T times lambda, will be same as the K choose T times the number of blocks B. So we have some parametric conditions satisfied whenever we have a T designs. Now, as I told you earlier, and our study stems from this partial geometry, so I'm going to recall the definition of partial geometry. And as a one design, we call geometric, a design is geometric whenever pair of points occur and most one block, one common block. So pair instant with and most one common block. So means either one block or no blocks. Then such a design we call geometric design. And here partial geometry satisfies another condition. Every anti-flag point, non-instant point block pair PB, and for any given such an anti-flag, if the number of flags, say Q and C, where Q comes from given block B and C contains the given point P, and then number, the total number of flags which whose point is from B and whose block consisting P, that's containing P, and then number is constant, then we said partial geometry with and parameter alpha, okay? So partial geometry, and every point, the lines has a K points, every point instant with R blocks, and where any given anti-flag P and B, there are the number of instant point block pairs are alpha, and that instant point block pair is supposed to have the point coming from B and block passing through the point P, that number. And I'm going to use that number a lot, so I'll show you the next page as well. And then we are talking about partial geometry. And that partial geometry, using 3 parameters, and because the number of points and number of blocks are depending on this given, and R, K, alpha with this identity. So usually they described by 3 parameters, R, K, alpha, or rho, kappa, tau in geometric notations. But here I'm going to use K and R and alpha because we are using this same purpose. Yes. Sorry, my telephone. Okay, go to the next page. Next one. Yes, so the usual 2VK1 design is also viewed as a partial geometry with alpha is equal to K, and you can easily check this. So the partial geometry is a geometric objects, but actually same as this 2VK1 design when alpha and K are the same, and otherwise they are different. So it has the partial geometry with many different sources, not only this 2 design. Okay, next. Now, if we extend this concept of partial geometry a bit, this is a Bose-Shimamoto's definition of what's called as known as a partial geometric design. And this concept occurs sometime in 1950s, late 50s and 60s. And here in our language, and I'm going to use a tactical configuration as a one design, one VVKR design. Whenever we do have such a design, and we can count a number of flags QC, where Q is coming from given block B, and C passing through given point P. And this number we are going to describe at denote it as a S sub PB. Now, and to be a one design to become partial geometric design with parameter alpha and beta, and this number SPB depends only on whether P instant with B or P doesn't instant with P is not instant with B. So whether PB are flag and all given flag PB, the number S, the number of flags QC, and with satisfying this condition, Q coming from the block B and C passing through the given point P. And that number is constant beta. If P is not instant with B, then that number should be constant alpha. In that case, the one design will be called a partial geometric design, and Neumaier also called it as a 1.5 design. And the reason he named it as a 1.5 design is one design requires the additional condition. The number of SPB depends on whether PB are flag or not. That additional condition is required. But if we go to the 2 design, then always and 2 design satisfies this condition. And so 2 design, if 2 design satisfy this condition, then because all arbitrary T designs with T larger than 2 also can be viewed as a 2 design. So all ordinary 2 designs and actually satisfies and this condition, meaning all T designs with T bigger than or equal to 2 is the partial geometric design as well. Okay, so in that sense, partial geometric design is a more general concept than ordinary T design with T bigger than or equal to 2. But this partial geometric design is also the sort of the concept, the generalization of the notion of partial geometry. And so in that sense, and studying the other sources of partial geometric designs beyond partial geometry or block designs is of our interest. And so we sort of find all other partial geometric designs, and some of those partial geometric designs may be classified under certain characteristics. So that's what we are trying to do in here. Okay. Well, so far, and do you have any questions? Maybe I'll give you a little pause a little bit, because this concept is new to some of you. So partial geometric design or 1.5 design is a one design, and which having this additional property. The concept is slightly different from ordinary combinatorial T designs, where, and when you're talking about ordinary combinatorial T designs, we are counting the concurrence number of the given set of T points. How many blocks having given T sets, contains given T sets. That concurrence determines ordinary combinatorial T designs. But when you're talking about partial geometric designs, and concurrence is the hidden, we only count and this number SPB. So given point block pair, and we count number of flags where points coming from given block B, and block contains given point P. If that number, and depends only on whether given pair PB are flag or anti-flag. If it is flag, that number constant beta. If it is anti-flag, that number is constant alpha. Okay, that determines a partial geometric design. But this condition is automatically satisfied for usual combinatorial T designs if T is larger than or equal to 2. Okay, that's what we need as a basic facts. Okay, now we are going into and other concurrences, the investigate concurrences of these partial geometric designs now. Okay. So before I going into discuss the concurrences, so ordinary T designs has two design has a unique concurrence. Every pair occur together in lambda blocks, just one number lambda. But partial geometric design, and we will see as a possibly two concurrences. Some pairs occur together in lambda 1 times, and other pairs occur together in lambda 2 blocks. And this number is maximum so far, and we know it is maximum 3 different concurrences though. And so towards that direction, and we need some of these basic identities to analyze further concurrences. So I'll briefly recall the parametric conditions of partial geometric designs. Yes. Okay, these are the third condition is for the non-triviality, and the beta plus 1 number is always bigger than or equal to k plus r, and always less than or equal to kr will be assumed. But if it is non-trivial and also proper ones, satisfies these 3 conditions. Well, the these things are the well-known results, so I'm going to move on. And also, we will work with instance metrics of the partial geometric designs as we did in the ordinary combinatorial T-design study. So N is an instance matrix whose rows are indexed by the points, whose columns are indexed by the blocks. So it will be V by B matrix. And whose entries are, of course, if it is at the point lie instant with a block, then that entry PB will be 1. If PB is an anti-flags, and the entry will be, PB entry of that instance matrix will be 0. So this is a 0, 1, V by B matrix. So if we multiply all one matrix J on the left, we are essentially counting the number of ones in each columns, so same as K. And if we multiply all one matrix on the right, NJ, we are counting the number of ones in every row, and their entry will be R, so RJ. And then when you multiply N transpose, and that will be V by V matrix if we go only up to NN transpose. But if we multiply another N transpose N, it will become V by B matrix. But if we check the entries of corresponding P and B, and the entry will be same as beta N plus alpha times J minus N. That beta and alpha, that number, S of alpha beta, S of AB for given point block pair, that constant number beta and alpha actually give us these entries. So, and N transpose N is always same as the beta N plus alpha N J minus N. Beta is the corresponding to the flag PB, and anti-flag PB, and alpha is, beta is a flag B PB, and alpha is anti-flag, so J minus N times alpha. Okay. So if you look at this for the first time, and it will take a little time to actually accept this one, but entry-wise, and you can easily verify that those two entries on the left and right will be the same. But this is our key identity we are going to use repeatedly in the rest of the talk. Okay, next page. And when you talk about concurrence, and I'm going to denote that number, concurrence PQ for the given points P and Q, as a number of blocks where P and Q occur together. This number can be also read from the entries of NN transpose. So if you look at the V by B matrix N times and B by V and transpose, essentially PQ entry there is counting the number of blocks which contains both P and Q. So this concurrence number is read from the entries of this NN transpose. So we are going to call NN transpose as a concurrence matrix of given partial geometric design. And if we need the individual numbers for given pair P and Q, we are going to use lambdas of PQ. Okay, next. And then we have the following identities. Okay, you can show all the way, yes, up to that. So these are all proved by Neumaier in 1980 and his paper on TN half designs. And as I introduced earlier, the Neumaier's term partial geometric design is nothing but 1.5 design. So he was looking at the T.5 designs by extending this similar concept, but I'll leave it here. And so if you look at, for example, second identity, the number SPB is from the entry NN transpose NPB, which is because NN transpose N is same as beta n plus alpha times J minus N. And we can read those entry PB there. And if we have to multiply another N transpose PQ and we can figure this out, and that number is a sum of product of PZ and lambda ZQ, PZ, ZQ over QZ, same. And if we take a products of all points Z in the point set and summing up, and that's the entries and N transpose squared. And if we express this one in terms of parameters, as you see at the right and bottom, and if P and Q are the same, of course, beta R, but for every pair P and Q, different pair P and Q, that number is same as N times lambda PQ plus alpha R. And N, I didn't introduce you earlier, this N is beta minus alpha. So, and sometimes I'm using beta minus alpha as an N. So we will use those parameters VB, KR, alpha, beta, and beta minus alpha, which is N, 7 of them, but of course, they are not necessarily independent, as we see so many identities between them. So usually 4 or 5 should be enough. Okay, next. As I told you earlier, and also the observed by Neumaier, and Neumaier observed that the concurrence number, lambda PQ, varies only up to 3. And he characterized when the concurrence numbers are either lambda 1 and lambda 2, and he characterized such a partial geometric designs and where those partial geometric designs coming from. And however, and although he gave us some of these basic steps about the calculating the spectrum of that concurrence matrix and some of these properties, but he didn't look at those concurrent 3 cases and either characterize or classify the partial geometric designs. Okay, go next. So when I say lambda sub PQ is in either lambda 1, lambda 2, or lambda 1, lambda 2, lambda 3. So I put the parentheses inside the ascent notation there. That means maybe and lambda 2 appears or may not, or maybe lambda 3 appears or may not. And that I express it that way. But so far, all known examples of partial geometric designs has at most 3 concurrences. However, and no one ever tried to prove that every partial geometric design has exactly 3 concurrent, and most 3 concurrences yet. So this is still open. But all known examples so far and has at most 3 concurrences. And we try to figure out all partial geometric designs with exactly 3 concurrences for several years. And I'll report some of those results later. If partial geometric design coming from ordinary 2 design with parameter VK lambda, as a partial geometric design, the parameters are the alpha is equal to lambda k, beta is equal to lambda k minus lambda plus r. And in this case, the concurrence number of any pair of points and as two design indicates, only one. So one concurrence number lambda. So if it is coming from two design or ordinary T designs, there is only one concurrence number lambda 1. Next example. And if it coming from partial geometry, the partial geometric design coming from partial geometry, and in that case, concurrence numbers are either 0 or 1, as the geometric property dictates it, because every pair of points either occur together in one line or not. So 1, 0. If it is coming from transversal design, and I'm not going to define transversal design unless someone asks. And we do have a concurrence number, again 2, but that concurrence number is either 0 or lambda, whether those pair belongs to the same block or not, or same group, or coming from the block. Okay, next. So again, and our goal is to analyze the concurrences and find all the partial geometric designs with a specific number of concurrences and characterize them. So in that direction, now we need this. The concurrence matrix and has 2 or 3 distinct eigenvalues, namely that spectrum, I can say one eigenvalue KR, and then sigma many eigenvalues n is beta minus alpha. And then eigenvalue 0 occurs 3 minus 1 times minus sigma. And when n is equal to 0, and of course it's automatically become 2 eigenvalues. Okay. And then when it's only 2 eigenvalues, lambda 1 and lambda 2, and in that case, and Neumaier count the number of points for given fixed point P and number of points Q, and whose concurrence number with P is lambda 1. So once we have this one, of course, we can find the remaining concurrence number lambda 2, because the case of 1 plus, and with those ones making it with lambda 2 concurrence with given P, if we call it case of 2, then 1 plus case of 1 plus case of 2 will make up total number of the points. So knowing one, we know automatically the other as well. Okay, next. There were the study of the Hu and Lei, and in their paper published in 21, they studied the same partial geometric designs with specific concurrence sets, the concurrence profiles, lambda 1, lambda 2, lambda 3. And in their the study, and they also noticed that when concurrence numbers are lambda 1, lambda 2, lambda 3, and different, whether lambda 3 becomes 0 or not, it doesn't matter. As long as lambda 1, 2, 3 are different, such as 2, 1, 0, or 3, 2, 1, I'll give you some examples. And using that, so pairs, they have in concurrence number lambda 1, pairs with lambda 2, pairs with lambda 3, and somehow gives us a partition of the whole set P cross P, as you can see, easily see. So the diagonal, the XX collection R sub 0, and R sub 1, those pairs of points P and Q, whose concurrence number is lambda 1, and R sub 2 as a lambda 2s, R sub 3 as a lambda 3s, and these 4 sets gives a partition of P cross P. And by using the Neumeier's result and extend it, and we can find those for each given fixed point and number of points that make a pair appear together in R1, R2, R3 as a size of Rix. I denote it as a collection of all points Y whose concurrence number with X, lambda xy is equal to lambda sub I, is K sub I, then, and not only gives us a partition, it also familiar to all of you knows association schemes. And this partition of P cross P as a relations, I wonder whether it gives us an association scheme. Yes, it is, but we need an extra condition. Okay, to prove this, and all we need is some analysis of these parametric the identities, which using the Neumeier's earlier identities. Okay, so go to the next. So, and they found Ku and Lei, their contribution is when lambda sub 3 happen to be R minus N, where N is a beta minus alpha. And actually, this partition gives an association scheme. So the question is, and find such a PGD, meaning and that produces an 3-class association scheme. And to do that, and here the condition, sufficient condition is lambda 1, lambda 2, lambda 3 distinct concurrent number, and lambda sub 3, the smallest, has to be same as R minus N. And one of such an example, the Ku and Lei gives this example, PGD, all PGD, 3R and 3/4 R squared, and 4n R with alpha 4, beta R plus 4, and actually meets such a criteria. So it gives us an association scheme. So as a particular example, when you take R is equal to 4, and these are the block sets of such a partial geometric design on 12 vertices, 12 points. And their concurrence numbers are, for example, 0, 1 occur together in 2 blocks, and then 0, 3 occurs only once, and as well as the others. And there are some pairs, 3 and 4 never, occurs once, but 3 and 5 occurs and again twice, and some pairs occurs none. So these are 3 concurrences with lambda 1, 2, lambda 2 is equal to 1, lambda 3 is equal to 0 case. Now we do have another example. So actually there are many examples known. And this is my student Ted Tranner found by using computer search with 8 points, 8 blocks, and block size 4, and the recurrence for alpha 6, beta 10. So it meets that criteria, and it gives an association scheme whose relations may be defined as if you take 4 as a 0, and 3-class association schemes whose relation table is exactly the same as the concurrence table NN transpose. Okay, so there are, and then the matrix NN transpose looks nice, but it is not circulant yet. But we do find a lot of partial geometric designs whose concurrent matrix become circulant. So the examples are over here. And so the partial geometric design with order 8, and one of them whose concurrence is a circulant matrix with first row of the concurrence matrix has entries 5, 2, 3, 2, 1, 2, 3, 2. So you circulate to define the NN transpose. And order 12, we do have this one, but the order 12 in this case, again, R minus N is equal to, beta minus alpha, that N is equal to 4, which is same as R. So it also meets the criteria for the partial geometric design, which produces an association scheme. So this second example, PGD 12, 12, 4, 4, 4, 8, again, gives us an association scheme. Now, what's special about this one is the concurrence matrix is a circulant matrix with the concurrences 2, 1, 0 again. But when you look at the third example, and this time point order is 12, block is 14, and unfortunately the R and N are different. So it doesn't give us the association scheme. However, the concurrence matrix happened to be a circulant matrix with first row entry 7, 3, 4, 3, 4, 3, 1, 3, 4, 3, 4, 3, like that. Okay, so this tells us that the wondering whether partial geometric designs whose concurrence matrix is the concurrences are 3 different ones, and all appear as a circulant matrix or not. And that was the problem my student Straner tried it. Unfortunately, all of these 3 students who studied these kind of things now works in a industry, not in academia. So I'm the only one who can present these kind of things in seminars and so on. They are all working either in telecommunications company or the national security space. Okay, go to next. As you know, if concurrence matrix coming out of the circulant matrix, the eigenvalues are easily calculated. We already have a formula for all eigenvalues for any circulant matrices. So we want to make use of this. So go to next. So for example, if on 6 point, 4 blocks, and whose concurrence matrix make this type of circulant matrix, and it gives a partial geometric design, and that coming from the transversal design with a certain parameter. And this one has a specific eigenvalues. Go to next. And so in general, we notice that if order is congruent 0 mod 2 with V at least 6, and there is a partial geometric design of these parameters. And that concurrence matrix happen to come up as the same type, and half V minus 1 and 1, and then half V minus 1 again, and then 1. And this concurrence matrix has a spectrum, and 2V minus 4 as a multiplicity 1, and V minus 4 as a half V minus 1, and 0 as a multiplicity half V. So 3 distinct eigenvalues. Okay, this tells us, and yes, goes next. And we using assume that the partial geometric design has a certain type of circulant matrix. That certain type here is a sort of the concave in the index, or you can say symmetric, C1, C2, C3, C4, C5, C6, and then go down to 5, 4, 3, 2, 1. Some behavior is either the modality, or you can call it symmetric property. If concurrence matrix coming this way, and we can find all partial geometric designs and from that concurrence matrix. So order 12 case, and we found out that there are at least 11 infinite families of partial geometric designs of order 12, whose concurrent matrices are all circulant. So these are the list of such. Okay, so these are the partial geometric designs with that circulant concurrence matrix characteristics. Now, this doesn't cover all known partial geometric designs of order 12. Actually, there are examples of partial geometric designs whose concurrence matrix is not circulant. So the question is, go to the next. And so far, all known partial geometric designs has at most 3 distinct concurrences, as I introduced earlier. So we still have this open problem, whether it is true for all partial geometric designs or not. And then next, our question is, can we characterize all partial geometric designs that having circulant concurrent matrix? Other way is, if possible, or even by using computer, that's okay. But parametric conditions and the properties of spectrum, and the result we introduced is, and for our knowledge, the kind of having a limit, because there is some other matrices, some other type of partial geometric designs. So that doesn't give us a complete solution. So we need to look at some other method. And if we do, and we can classify all partial geometric designs having circulant concurrence matrices and so on. Okay. Well, there are the other way around. Partial geometric designs obtain as simply the relations as the adjacent matrix as instant matrices, and there are such an association schemes, but due to time, and I have to stop here, and can we have just a minute or two if you have any questions? I'll stop here. Yes.
Okay. Thank you for your talk.
Mm-hmm.